In this lesson, we're looking at quartic functions. Now there's a few ways that we can look at this, and to begin with, we're going to think about this in that turning point form. Now this behaves very, very similar to quadratic functions in that my turning point is defined by hk. So that's whatever we see there and there. It's also true in this form that we can imagine that k is what's been translated. So we could say that it's translated k units in the positive direction of the y-axis, provided k is a positive number. It's also true that h governs our translations along the x-axis. So if we see minus h, we would say that this is translated h units in the positive direction of the x-axis. So the big thing to remember here is that my turning point is at hk, and that this graph looks effectively like a more flat parabola. So with our first example here, we're asked to sketch the graph of x minus 1 to the 4 minus 2. Now just make my axes appear there. So we can first read that the turning point here is at 1, negative 2. So that's my turning point. We also note that there's a number 1 here as my a value, so the shape is a positive quartic. Now immediately, if I mark that 1, negative 2, so I'll go across 1, down 2 and say that's somewhere about here, and I recognize that this is a positive shape, you can see that I'll have two x-axis intercepts and also a y-axis intercept. So to find the y-axis, which is what we'll do first, we're going to let x equal 0. So y is 0 minus 1 to the 4 minus 2. Now you may want to notate this with a subscript I for intercept, so the examiner knows what you're doing. So this is equal to negative 1 to the 4 minus 2, which is 1 minus 2, or negative 1. So I can see that I've got 0, negative 1 as that y-intercept. And that's going to be a bit difficult to see once I've sketched my graph, so I'm just going to rewrite that on this side. So looking at my shape now, you can think of my quartic as a rough shape like that. It's a little bit tougher with the digital pen, but you get the idea. And we still need to find our x-intercepts. So I'm thinking that my x-intercept, minus 1 to the power of 4 minus 2, is equal to 0. So this gives me, I guess, the general equation that we let y equal 0 to find our intercepts. If I add 2 to both sides, the x-intercept minus 1 to the 4 is equal to 2. Now the opposite of to the power of 4, the way I'll get rid of that is I'll raise both sides to the power of a quarter. That is, I'm taking the fourth root of both sides. So this is the fourth root of 2. Now, because we've got an even root, we'll think of this as both plus or minus the fourth root of 2. And so finally, my x-intercepts are 1 plus or minus the fourth root of 2. Now I know that the fourth root of 2 has to be more than 1 because one of my intercepts is negative. Also, 1 squared is 1. So to get something bigger than that, I need to have it bigger than 1. So this first one will be 1 minus the fourth root of 2. And this one here will be 1 plus the fourth root of 2. Now it's important that you recognize that my shape is very, very poor here, but it's a little bit difficult for me to sketch it with this pen, and I'm hoping that you guys will get something that looks a lot more even, accurate, and matching that shape. It's exactly like a parabola, but with more of a flat base there. It's also important that we label y equals x minus 1 to the 4 minus 2. In this example, we have much the same graph. We can see from the value of a equals 1, from the fact that there's no number out there, that this graph is going to be positive, and it's going to look like this shape. It's a bit like a beaker. What we note though is that my turning point is -1, 2. So we've always got to do the opposite of the sign we see inside the brackets. So if I go -1, so 1 to the left and up 2, so there's -1, 2, and I think that this is a positive parabola, I can already tell that there will be no x-intercepts. So I can go right ahead and sketch the shape. Now to find the y-intercept, I'm just going to let x equal 0. So letting my y-intercept where x equals 0 gives me the fact that y is equal to 1 plus 2, which is 3. So in this case I'll have 0, 3. And that's about it. The only thing we'll need to do is label our graph y equals x plus 1 to the 4 plus 2. So we can see that there is another form of a standard type of quartic graph. So another standard equation looks like this. Now I've used A, B, C's and D's and E's, but I actually would rather that we think of this as y equals A outside of x minus the first intercept, x minus the second, x minus the third, and x minus the fourth. So in this regard we can remember that if we let y equal 0, we'd be using null factor law. And so all these brackets would represent x-intercepts. Now you might be thinking that the previous two graphs only had 2 x-intercepts. How can we suddenly have 4? And it's because graphs of this shape look like this. So you can think, if the A is positive, we're winning. So that means that A is greater than 0. However, if the A is negative, we don't like negatives, and we're miserable, and we'll get something that resembles an M. So we're being asked to sketch x minus 1, x minus 2, x plus 1, x plus 2. The first thing I'll note is that being in intercept form, being in the form of 4 linear brackets, or 4 linear factors, and noting that A equals 1, we're going to be winning. This is going to be a nice positive quartic. I should also note what I can instantly see, and that is, if x minus 1 equals 0, then one intercept is 1. If x minus 2 is 0, then the other intercept is 2. So I'm just using null factor law here to show that if I let all of these brackets equal 0, I'm going to get my intercepts. So I've got an x-intercept at -1, -2, +1, and +2. So we'll quickly draw up some axes. Pretend I'm drawing a straight line there and there. We've got x, we've got y, and we know that we should have -2, -1, +1, and +2. Now these are all evenly spaced, so my curve should have a maximum at that y-intercept. Now it's not always guaranteed this to be the case, and I'm taking a guess here being a non-calc, but I'm going to say that that stationary point occurs where x equals 0. It's also the y-intercept, so it's worth labelling anyways. We can think y is equal to 0 minus 1, 0 minus 2, 1, 2. So -1 times -2, which is +2, times 1 times 2, which gives me the value 4. And so y equals x minus 1, x minus 2, you get the rest. We could label that graph. Now sometimes we'll have something like ax squared. We might have something like ax minus x1 squared, x minus x2, x minus x3. Now what we're thinking about here is that this thing here is one repeated solution. In other words, wherever we see that squared as a product of linear factors, we're saying that that must be a turning point that's also on the x-intercept. So if I'm looking at y equals x to the 4 minus 2x squared, my first step would be to factorize this. Now the reason is, we want to factor the expression so that we're either in one of the two standard forms we've looked at. Either we're in a turning point sort of form, or we're in that intercept form. When quartic functions are in standard form, as this one is right now, it's not much use to us. So if I take x squared out as a common factor, I've got x squared minus 2. And if I continue to factorize that, I've got x plus root 2, x minus root 2. Now this is from the difference of two squares, that a squared minus b squared. Because when we factorize something squared minus something else squared, we end up with a plus b, so the square root of each thing, a minus b. And that's what I've got here. So right away, what can we tell? Well, we can see that there's a repeated solution at x squared equals 0 or x equals 0. So there's a turning point on the origin. I know that there's an x-intercept at negative root 2 and an x-intercept at positive root 2. So if I quickly sketch up an axis, pretending that I've used a ruler for those straight lines, at y we've got x. I know that there is a turning point here at 0. I know that there's an intercept at negative root 2 and one at positive root 2. Now this has to be a positive curve because the leading coefficient here was a positive number. So that means this is going to look like a W. Now the only way I can join all these lines together in the shape of a W is if we look like this. Now you might be wondering, should this point and that point be even? Well, it certainly seems like it at this case, because the x-intercepts are equidistant, but we couldn't be sure of that without using calculus. So we don't have to worry too much about whether or not those two troughs meet up exactly, although I think you'll find in this case they probably will. It's important also that we label the graph. And we don't have to worry about the other stationary points unless we had a calculator to help us, or unless we've already covered calculus. We're assuming in this case that we haven't. Sometimes we might get the case that we have two repeated factors. Now, all this means is it's the same shape, but there are two turning points on the x-axis. So this might be B and this might be C. Ultimately, though, that we've got the same shape. So whenever I look at a curve like y equals x minus 1 squared, x plus 2 squared, I know at x equals negative 2, it's both a turning point and an intercept. And at x equals 1, it's both a turning point and an intercept. Now to see what this looks like, I'll need to sketch an axis again and put in my repeated solutions of negative 2 and 1. Now the only way I could make a W is exactly the same shape like that. So I've gone here, and we can pretend that I've just hit that more appropriately. Now I won't know what this value is. It's not necessarily going to be negative 1/2, but I can find this y-intercept there. So if we let x equals 0, I've got minus 1 squared times 2 squared, which is 1 times 4, or 0, 4. x, y, and then don't forget to label the graph. So that's how we deal with repeated solutions. The next thing we're going to look at is what happens when one of those linear factors is cubed. Now when we see this, this will be a point of inflection. Now, in order to put that in the context of the whole quartic, the quartic will either have a point of inflection here, so that's my three-peat, or the same positive graph can have the point of inflection there. So it really depends on where that repeated solution is, if it happens first or second. It seems like it would change the shape, but really, as x approaches infinity, y approaches infinity, and x approaches negative infinity, y also approaches infinity. So the same basic shape hasn't changed. When I look at this curve, I can see, okay, I've got an a value of 2, so it's still positive, but I might need to make sure I've got enough points to represent the dilation. I can see that there's a three-peat solution at x equals 2. So at x equals 2, I think point of inflection, and there's one intercept at x equals 1. So drawing up my axes, I've got x and y. We can think at x equals 2, over here, there's a point of inflection. At x equals 1, there's an intercept. Now the only way to make that positive curve is if we have this shape here. So I need to come down. I've got a turning point and a point of inflection. Now I want this to continue as I'm going to hit the y-axis. In order to find that, we might think y equals 2 times negative 2 cubed times negative 1. And that's going to be 2 times negative 8 times negative 1, which is 16. In order to make sure we get the marks, we should also sketch this curve. And just for surety, I might fill out these intercepts there. With 3 points, I'd say I've done enough to show this dilation. Now here we have a quartic in standard form. Now it's trying to give us a hint as to what we can do here by telling us to find the coordinates of the points where the graph crosses the x and y axes. Well, the y-axis is easy. That's just going to be done by letting x equal 0. So that's 0 minus 0 plus 1. You can always recognize that from there. So my y-intercept is 0, 1. Now the much harder thing to look at is what will my x-intercepts be? We haven't looked at how we solve these standard equations. But you might recognize that this is actually 3 terms. It's what we might call trinomial. And you've probably guessed it at this point, but where else have we seen trinomials? It's in the study of quadratics. Now if I had x to the 4 minus 2x squared plus 1, I can make a simple substitution. Suppose I let this term, the term next to my second term, suppose I said that let's let a equal x squared. Well, x to the 4 is x squared squared. So that's just going to be a squared minus 2a plus 1. Now I have a quadratic, and I can solve for that quadratic equal to 0. I might recognize the factors of 1 that add up to negative 2 is x minus 1, x minus 1, which equals 0. And if I'm looking at this expression, I've used x, my apologies, I should have used a. I can see here that a is equal to 1. Now, what is a? Remember that we said let's let a equal x squared. So if I replace that with x squared is equal to 1, I can see that x, or my intercepts, are plus or minus 1. Now, I might also recognize that this is a repeated factor, or rather both plus and minus 1 are repeated factors. So, if I draw out my axes, I've got plus or minus 1, and I've got 1 as my y-intercept. The only way to draw these together in a positive way is to make that w. We've got x, y, and now we've sketched something in standard form. So it's always really, really important that we're able to recognize quadratics even when they're not as straightforward as we might imagine. In this question, we're asked to fully factorize something that's all the way out in standard form. Now, you'll never be asked to do this by hand, so all we need to do is get out our calculator. We can press Action, Transformation, Factor, and then Factor again. Now, we just have to type this in exactly as we see it. So I'll do that now. So as you can see, we've just typed that in. I'll now press Execute just at the bottom, which is that button there. And we've got this fully factorized. If we had something that wasn't a very nice form, or we suspect it could be simplified further, there's a simp button just here. Now, if it could be simplified, it would there. So what have we found? We know that this is equal to x plus 2, x minus 1, x minus 2, and x minus 3. So from here we'd be able to sketch. Let's now imagine we're given this question here. It's the same function. So if this was non-calc and we were given the information prior, we know that this function is equal to x plus 2, x minus 1, x minus 2, x minus 3. So that is x plus 2, x minus 1, x minus 2, x minus 3 is equal to 0. From here we can see it's just a matter of using null factor law. I'd like to give my answer in set notation. So x is an element of the set of numbers, and we'll just give these in ascending order. So minus 2, 1, 2, 3. Now that's easy enough. Suppose we had to solve 2a to the 4 minus 5a squared minus 3 equals 0. Well, we've got this in standard form, but you may recognize that we again have a trinomial, and that middle term is something squared. So let's this time let x equal a squared, so that I have 2x squared minus 5x minus 3 equals 0. Now if I factor the left-hand side, well, AC is negative 6. The factors of negative 6 that add up to negative 5 are negative 6 and 1. So 2x squared minus 6x plus x minus 3 is equal to 0. Now I can factor that. And if I take 1 out as a common factor there, I can see I've got 2x plus 1, x minus 3 equals 0. And if I wanted to solve these, either x equals negative a half or x equals 3. But when I resubstitute for a squared, something squared can never be negative a half. I can't have taken a number, multiplied by itself and got a negative answer, because two negatives make a positive. Another way to think about this is a can't be equal to the square root of a negative number. So we have to ignore those solutions. Rather, let's pursue the fact that a squared equals 3. Well, if I square root both sides now, a is plus or minus root 3. If I give that in set notation, a is an element of minus root 3, positive root 3. And so let's revise what we've learnt. We can sketch quartic functions in 3 forms. That is, We've looked at intercept form, we've looked at some in standard form, and we've also looked at turning point form. Now, far and away the easiest might be turning point form, although if we can factorize something, we could always get it into intercept form. We know we can factorize some quartic functions, especially using technology, and also when they mimic the pattern of a quadratic. We can solve quartic equations using null factor law, and we can recognize the long-term behavior, I've just realized a typo there, of higher order polynomial functions. That is, quartic functions that are positive should approach infinity no matter which direction we move in the x.